A warm good afternoon to everyone. We would like to thank 𝗏𝗏 for giving us this opportunity to present one of our digital initiative, that is Digital Twin, which we have implemented in exhauster of Coke Oven. I'll give overview about our company. We are a flagship company of $23 billion. Sure. So we'll wait for the jury member to join us.
Sorry to pause.
Should we continue?
Okay, I think he's here. Carry on.
So, we are the India's leading and one of the world's most efficient integrated steel maker. We have state-of-art upstream and downstream operations spread across the country. Our vision, purpose, value is as shown. Presently, we are operating at the capacity of 34.2 MTPA. We have expansion plan of 50 MTPA to reach 50 MTPA by the financial year 2030-31. We are spread across various states of country. We have our presence in Europe and USA. The products at Dolvi Works are as shown: HRC, HR plate, slab, TMT, and pellet. Regarding the team composition, our facilitator is Mr. Shekhar Salil. Our leader is with us, Mr. Mukul. Member, Mr. Rohan, he is also with us. Mr. Dinesh, Mr. Rahul, Mr. Mayur, and self, 𝗍𝗵𝗍 Pardesi. So I'll give you overview about the coke oven process. We get the raw material, that is coal, from RMHS, which is then carbonized in batteries. The various gas, during this process, various volatile gases are emitted, which are captured by the exhauster. Exhauster is the heart, or is considered to be the heart of coke oven. It catches all the volatile gases, processes, and send it to the cleaning unit, where these gases are cleaned, and these gases are then further sent to various plants for utilization. Now I call upon Mr. Mukul to take forward the presentation.
Good afternoon, everyone. As you see on the left side of the window slide, the major components of the exhauster are shown: a motor and gearbox coupling and fluid coupler and the blower. The tripping of the downtime minutes and the frequency of the breakdowns, the details of the breakdowns in last 4 years has been shown. As you can say, the last year in 2024, it is the tripping of the 447 minutes and number of breakdowns are 4. The theme is we want to achieve equipment reliability of higher side by reducing the number of the breakdowns, proactively addressing irregularities and minimize downtime and maintenance cost, analyzing the variations in temperature, vibration, and continuous critical equipments monitoring using real-time data, and the implementation of the pre-warning goals to enhancing the maintenance insights, improving access to real-time data, avoiding gas wastage and other byproducts getting from the coke oven gas. The existing sensors of the installed in the equipment is insufficient for tracking minor spikes and abnormalities. Automatic pre-warning and accurate prediction systems are not available, or it is very critical of nature as the failure of this equipment. Here you can see in the picture where the failure of the equipments dissipate the gas in the environment. That the flow chart outlines the challenges and potential causes of the plant downtime. This aligns goals and identify potential issues in the process. Primary challenges identified includes critical equipment issue, tar formation, vibration, and harsh conditions. Their issue lead to high manual interferences, partial compliance with the monthly schedules, and lack of valid data analysis. The accumulation of these challenges result in an equipment breakdown and subsequent plant downtime. Our target for the financial, we have targeted for to reduce the downtime by 88%. The target downtime is 60 minutes. For the 25 key initiative includes motor, blower, gearbox, and fluid coupler health monitoring, as well as the data integration into monitoring and prediction analysis tool. To achieve our goal for reduction in the downtime, we sit across our cross-functional team for the brainstorming session, and the major questions asked during this brainstorming sessions are how we can acquire the data, what type of vibrations can we utilize. Although the existing vibrations are installed, but they are not with that high sensitivity, so that we can predict or use predict. What will be ensure the data is taken during the actual running of the motor only. So we go with the motor RPM as an indicative. The certain RPM, if motor is running above the certain RPM, it is taking that the motor is running. Cost is also a concern, but as the equipment is in very critical for the nature of critical in nature, so we decided to go with the project. And these are the timelines to complete the project in initial while during before the inception of the project. So we started in April 2024 and targeted to complete the project by April 25. So after the brainstorming session, we come up with the proposal number 1, set using of existing sensors and make dashboard in OSI Pi. But this Pi system dashboard is limited for the real-time data and some history of the data for a longer period, but there will not be any prognosis analysis, and failure mode analysis is not available for Pi. So we are not getting so much benefit for the equipment to prevent the equipment failure, or preconditions, pre-alerts are not available. So then we come up with the proposal 2, the second proposal, that we use MCSA motor current signature analysis relay and tri-axis wireless vibration system along with the oil contamination sensors that will be used with our existing data or feed into the analytic engine. And that analytic engine will enable us to provide a detailed analysis of vibration, temperature, and motor current signature analysis. Motor current signature analysis. Sorry. And we will get a pre-alerts for the system. And these are preparation for implementation. We have as identified the critical equipment as exhauster. Then we go for a vendor evaluation for our requirement, and after the we do the site survey for critical equipments with the vendor for oil, and then we get sensor installation and configuration of the dashboard, and we go live in the detailed analysis. We started reporting in February 2025, which we achieved before our set target. And this is the condition of the after the completion of the project. As you can see, the before implementation of this digital twin project, we have only the level 1 SCADA system that we have some limited access to the real-time data, and it is not able to give any pre-condition alarm or prognosis for the system. But after the completion of this project, along with this level 1 SCADA system, we are able to get the temperature with the triaxial vibration system, and all particle sensor was installed. So we give some system is able to give some insights of the system or condition monitoring system, prognosis for the system. So we are able to run this machine without breakdowns. And now Mr. Rohan will take care of it.
Thank you, Mukul sir. So now I will be explaining the digital twin concept. So a digital twin leverages synthetic data generation, which involves retaining the data collected from the field sensor and utilizing our domain knowledge of machine operations, in this case exhausters, and then incorporating this data to train various models that accurately represents the behavior of a healthy exhauster unit. The ML model here we have used is random forest classifier in the vibration analysis, and then MCSA, which is analyzing the healthiness of the motor unit. So here's a detailed animated video of the exhauster, and here we will show you what sensors we have used and what insights they are giving. So firstly, the MCSA, the motor current signal analysis, is giving us the mechanical aspects on the motor and also the abnormality inside the motor. And here is the fluid coupler, which is in which we have installed the vibration sensor and the oil particle sensor, which is giving an insight on the bearing health and the oil health, as this fluid coupler and the gearbox, which is connected to the fluid coupler. Both are of circulating oil nature. So the oil's contamination, the oil is continuously circulated through a filtration system, and we are also monitoring the oil contamination. And now moving forward to gearbox, here we have installed vibration sensor and again oil particle sensor, which is giving us insights on the broken tooth and chipped tooth and all and the oil health. And here, after connected to this is the induced draft fan, which is responsible to fetch the volatile gases from our CocoOne battery units. So here we have installed two vibration sensors, one on the D, one on the ND side, and this gives us insights on the tar deposition on the impeller units, and also if there's any misalignment in the induced draft fan unit. So here was the animated model of exhauster unit. Moving forward, we did a cost calculation before the inception of the project. So the major, so the average time was a total of 6 hours in the past few years. So we calculated the losses of the valuable CocoOne gas, loss of tar and benzol. So these losses cumulatively came to 87,95,500 rupees, and the capital cost for implementation of this project was 1.2 CR. So after calculation, after this we calculated the ROI, which we would achieve in 16.3 months, and we are already halfway there. And till date, we haven't got any breakdown after implementation of this project. So that is the tangible benefit, 0.87 CR. And also, in intangible benefits, JSW as a group believes in sustainability and protection of the environment around us. So the coke being a very volatile component, and the gases emitted are also very volatile, which when emitted onto the atmosphere due to the breakdown of this equipment damages the flora and fauna in and around our unit. So with the reduction of the breakdown of this this particular equipment, we prevented that. We also got real-time alert notification when any abnormality arises in the equipment, and also enhanced maintenance insights which the digital twin system is giving us right now. In terms of standardization, we updated the operational procedures to for evaluating the predictive and schedule maintenance. We standardized the data collection logs, and we also imparted trainings to our teams and users. So this is the architecture of the sensors installed at the field. There are 4 wireless vibration sensors installed at the exhauster and all the connected components. There are 2 oil particle sensors, which and these are all connected to our database server. The database server is pulling the data from those sensors. And here's the architecture of our the data which is being pulled from our DCS systems, and the MCSA system, which is directly fetched, pulled to the cloud, where the machine learning model is currently being run. So here we have explained how the ML model is being trained. So let's say in impeller, we have a synthetic healthy impeller data and a faulty data. And this data is complied and continuously monitored with the live data which is being fed from the field, and it had been trained to compute the data within the time and frequency domain, and the hyperparameter tuning is done. And here we have explained the concept, what was the problem, that we were losing the valuable coke oven gas, which is also used as a fuel for our customer plants inside the unit, the production losses which were occurring due to it, and this solution, the exhaust digital twin, which gave us the monitor the exhauster's health in real time and have predictive and prognostic insights on the failures of the motor, gearbox, and impeller. And these are the list of sensors that we used. So we utilized this wireless triaxial vibration sensor, which has a scan time of 6 kilowatts that gives us the capability to capture the minor spikes in the vibration that are occurring. This oil particle sensor utilizes the ISO 4406 concept of gravitation method for oil contamination sensing, and the MCSA module, which is using the raw signals of voltage and current to perform frequency domain analysis. Here we have explained the oil particle sensor, and this sensor is capable to report the particle counts per 1 milliliter. And again here, this showing the MCSA, the motor current signature analysis. It's capturing the voltage and current, and on the frequency domain analysis, is doing the able to predict any mechanical failures and abnormality inside the rotor, motor, that is stator problems. So lastly, on the reflection and learning, we got to enhance the predictive maintenance, reducing downtime. We did real-time monitoring. We had detailed report analysis, and with this project, we reduced the breakdown significantly. The learning part, we learned of implementation of these new sensors and integration of it into the cloud system, and we used analytical approach, our analytical approach to maintenance enhanced. And our future plan is to install these predictive models inside the coke oven battery and all process critical and production critical plants inside our unit. Thank you.
Thank you, gentlemen. Good afternoon. You did wake us all up after the good lunch. I have a couple of questions for you. One of them is, there's a good glimpse of what the sensors are and what tools they're using, but how did you integrate them to make an analysis finally to say, this was the challenge with the coke oven battery and this was the challenge with which you had faced? I mean, how is the analysis done from with your digital twin learning?
So we have integrated our existing process parameters, which includes the temperature of the various units and bearings and other parts of the exhauster. And we needed to install these new sensors because we were not having this high scan cycle vibration sensors, with, due to which we are not able to detect the minor spikes. So, regarding how we are able to detect this, how the prognostic capability is working. So, this is a machine learning model, and this model basically is trained with the synthetic data of a healthy exhauster unit, and then it's been also fed the faults also have been simulated. And the live data which is being captured is then compared to this trained model. And then if any abnormality occurs in the live model, it is able to detect it early and then give us those things.
So I would like to add upon, while creating the model, we have worked upon 3 data sets. Initially, we have obtained the first data set from the system, which when the plant is running normally. Then we have created this simulated database, depending upon we have tweaked with various parameters, and we have found the results wherein the system can, if the fault occurs, we have simulated the cases that if these parameters vary, what all will be the results. And then we have deployed the model using the live data from the system.
My second part is, was this whole exercise done completely in-house, or did you have the help of some other OEMs to help you with this process?
Yes, sir, we have taken the help of Bosch in developing this.
Thank you.
I think you answered my question. My question was more related to what is your confidence level on the model working and what did you do to test it? I think you already answered it. Thank you very much. I think we'll leave the audience more questions. Very interesting case study.
We have a question from the audience.
Check. Yeah, thanks for the wonderful presentation on digital twins. Actually, this is the way the industry is going forward. My one question was that, like, you have introduced sensors, and finally you could mimic that particular machine. But how did you actually prevent failures? Because that is actually giving you an indication of early indication of a failure based on the various sensors and the models that you have done. But until and unless you do something to the process, really, how are you preventing failures?
Sir, how did we prevent the breakdowns? So earlier, the breakdowns were being caused by various issues, like we described, tar deposition on the impeller. So this was depositing upon a certain time, and after a certain time, when the vibration was at a certain level, there is a chance that the tar deposition is not even on the impeller. So there was a chance at a certain time some kind of deposition variation may occur, and that may create a spike, and this spike will cause the exhauster trip. So that was one case. And apart from that, we have installed the oil contamination sensor. So this instance also occurred, that there was a deterioration of the gears due to oils getting contaminated with the metallic parts. And this also caused a sudden rise in vibration, a sudden rise in spike. So this is again with the spikes of vibration that we were not able to detect with our existing systems, that is integrated with our DCS. And one more thing is the motor's behavior. So the motor's bearings are greased. So we have, as a maintenance practice, we have scheduled time with on based of run time to do that, to do the greasing of the machines. So in that as well, we got the prognostic insights. So, yeah.
Thanks.
Yeah,
So,
I would like to add on this. Like, there are 4 exhausters. Currently, at a time, 2 exhausters work. So this generates the alarms, and whenever the alarms are generated, we take the preventive measures to avoid the breakdown.
got it, yeah. So basically, you could reduce the downtime, because earlier maybe the failures were more severe because you didn't have a predictive model. So now you can catch it early and then do small maintenance and come back fast. Thanks very much.